I wanted to send out a review really on vertical asymptotes that I think we just, I don't feel like we got through what I want to the level that I wanted to get through in class. You know, recall that a vertical asymptote is a place where the function is undefined, right? And where do you see those places? You see them with division by 0 for rational functions. Okay, typically. So we're going to expand our understanding of vertical asymptotes. And instead of just setting the denominator equal to 0, you need to look at limits, okay? So when you have an infinite limit, you have a limit that looks like this, right? And we went through this today. As x approaches some value, that function is going to go to plus or minus infinity. And if that's the situation, then the equation x equals a, right? X equals a, that is the vertical asymptote equation. So that's your vertical asymptote. So an infinite limit is a vertical asymptote. That's the bottom line. So I want to go through the example that we had at the end of class today because it's got a wealth of information in it. And the question that we had at the end of class, grab another pen, was you were asked to find all vertical asymptotes, right? And they're always written in the form x equals a of the function that was given. And the function that was given was x cubed minus 10x squared plus 16x divided by x squared minus 8x. I need to pause there for a minute. So setting the denominator equal to 0, you should notice that x equals 0 and x equals 8 is a potential vertical asymptote. And I'm saying the word potential because to really determine if it is a vertical asymptote, you have to look at the limit as x approaches a. So when you set the denominator equal to 0, what you're finding are potential vertical asymptotes. Okay? Potential vertical asymptotes. You need to look at the limit to determine if they really are vertical asymptotes. So let's do that. Okay? So I want to look at the limit. Let me grab green. The limit, this is a equals 0, right? And here's a equals 8. So I want to look at the limit as x approaches 0 of the function, all right, which I'm going to write it as, we have to work on this and factor it out. Whoop. And we need to look at the limit as x approaches 8 of x cubed minus 10x squared plus 16x over x squared minus 8x. So we know the bottom factored into x minus 8. And up top, this is going to factor into x squared minus 10x plus 16. which can be factored again. The x's are going to go away, which can be factored again to x minus 8, x minus 2 over x minus 8. And that goes away. So you're left with simply, right, x over 2. So this becomes the limit. I should have left more space. And the same thing here, right? This is now the limit as x approaches 8 of x minus 2. So we have two limits that we've got to evaluate. Scroll here. We need to look at the limit as x approaches 0 and the limit as x approaches 8 of x minus 2, because that's what the function reduces down to. And you hopefully quickly see that this limit is negative 2 and this limit is 6. Neither of which, right, neither limit is an infinite limit, meaning neither of them go to plus or minus infinity. So there are no vertical asymptotes. There are no vertical asymptotes. In fact, we can take this a step further and say that x equals 0 and x equals 8 are holes in the function. So when you set the denominator equal to 0, those points, okay, or those exception points, are going to be either vertical asymptotes or holes. And it's up to us to determine if they're vertical asymptotes. And how do you determine if they're vertical asymptotes? You take the limit. And if they are not a vertical asymptote, then they're a hole. Okay? So hopefully that clears things up.